Welcome to This Explainer. Today, we're moving way beyond those dry textbook definitions to look at the gritty, mechanical reality of eventual consistency under high-scale production loads. If you're building systems at scale, you already know that slowness and failure aren't rare anomalies. They're basically the baseline. We live in a world where network packets just disappear, memory maxes out, and random garbage collection pauses completely stall our perfectly optimized code. Every senior architect intimately understands the absolute pain of dealing with random timeouts, phantom data, and the dreaded customer double charge. But how does that failure actually manifest under the hood? And more importantly, how do we architect around it? Well, that is exactly what we're breaking down today.
Okay, here is our roadmap for today. First, the consistency spectrum. Second, the anatomy of replica lag. Third, caching in stale data. Fourth, conflict resolution in idempotency. And finally, number 5, the real-world user impact.
Part 1. The Consistency Spectrum. From CAP to PAC, LC.
All right, we all know the CAP theorem. It's that foundational rule forcing us into a hard choice between consistency and availability the exact second a network partition happens. I mean, think about it. What happens when a backhoe literally severs a fiber optic cable between your US East and US West data centers? Or a core router just completely dies under heavy load? In that exact moment, you have to choose. Do you fail incoming requests to guarantee nobody reads out-of-date information? Or do you keep the app highly available, explicitly serving potentially stale data to your users? But focusing only on what happens during a catastrophic failure kind of leaves out a massive piece of the architectural puzzle.
To get the full picture, we need PACEL-C, and this theorem brilliantly illustrates a much harsher reality. The ELC part stands for else, latency, or consistency. It basically tells us that even in a perfectly healthy system with zero network partitions, we are constantly forced to trade lower latency for weaker consistency. Even without a severed fiber line, we're physically limited by the speed of light. If a user in Tokyo queries a primary database in Virginia, you literally cannot have both a 10-millisecond response time and strict globally synchronized consistency. You either trade away latency to get that consistency, or you trade away consistency by reading from a closer but maybe slightly out of sync read replica.
Consider the stark contrast in how we handle this trade-off. On one side, we have CP systems, or strong consistency systems, like TDB or CockroachDB. They protect a single source of truth using strict distributed consensus protocols like Raft or Paxos. If things get sketchy or a node is acting a bit slow, these systems will actively delay or just outright reject incoming requests to maintain 100% accuracy. On the flip side, AP systems completely prioritize responsiveness. They accept temporary inconsistencies, effectively absorbing network delays through background, asynchronous reconciliation. They're making a bet that it is way better to give a user a fast answer right now, even if it's slightly outdated.
Part 2. Anatomy of replica lag, the mechanical reality of AP systems.
So when we choose that AP path and rely on asynchronous replication or message queues, we inevitably introduce lag. Using Apache Kafka as our prime example here, let's walk through the exact mechanical lifecycle of a consumer group rebalance. Picture this. A single batch of messages takes too long to process because of a slow database write, and a consumer misses its max poll interval. Bam! That's your trigger. The Kafka group coordinator just assumes that consumer's dead. It revokes all partitions, forcing every single consumer in the entire group to send a join group request. Then, a leader is elected to run the partition assigner, which creates a brand new distribution plan. The coordinator syncs this plan back to everyone, and finally fetching resumes. But here's the kicker. This entire 5-step process is a stop-the-world pause. Absolutely zero messages are fetched during this time. A minor 1-second pause can instantly translate to hundreds of thousands of backed up messages, and your consumer lag just rapidly balloons out of control.
And the math behind tail latency reveals a pretty harsh truth about distributed systems. Variance multiplies. Let's say a single user request fans out to 10 microservices or database shards, and each shard has just a tiny 1% chance of hitting an 80-millisecond delay. Basic probability dictates that the chance of a fast, delay-free request is 99 to the power of 10. That equals roughly 90.4%, which means almost 10% of your total user requests will be slow. They get degraded by that one single straggling shard. You aren't just dealing with average latency anymore. You're battling the multiplied tail latency of your absolute slowest component at any given microsecond.
Part 3. Caching and stale data. Managing memory visibility.
When we try to use caching patterns to mask all this latency, we run into some strict architectural trade-offs. Cache aside is the industry standard, sure, but you're going to hit the database and take a latency penalty on every cache miss. Write-through guarantees strong consistency because you synchronously write to both the cache and the primary database, but you end up paying a very high write latency penalty for that synchronization. Write behind is super fascinating for high-scale ingestion. You write to the memory cache instantly, return a success to the user right away, and then update the database asynchronously later. It gives you ultra-high throughput. But if that cache node loses power before the database persists the data, that data is permanently, unrecoverably lost. Gone.
But what if you actually need ultra-low latency without all the risks of complex distributed caching? Well, we look to a concept called mechanical sympathy. This basically means designing software that aligns perfectly with how physical CPU architecture actually works. See, modern CPUs use L1, L2, and L3 caches, reading data in 64-byte chunks called cache lines. If two different threads modify two different variables that happen to sit on the exact same cache line, the CPU is forced to invalidate the entire line across all cores. We call this cross-thread false sharing, and it's a massive source of micro-latency. The LMAX disruptor framework solves this so elegantly. It uses a pre-allocated ring buffer and literally adds dummy variables to pad its sequence numbers to exactly 64 bytes. This guarantees each number sits on its own isolated CPU cache line. You trade a tiny bit of memory to completely avoid cache invalidation, and it unlocks insane nanosecond-level lock-free throughput. It's a real game changer.
Part 4. Conflict Resolution and Idempotency. Surviving the retry storm.
I want you to ask yourself a fundamental systems design question right now. A user hits pay on your mobile app. The network hiccups right as the request leaves the device. The server processes the payment, but the success response gets dropped over the cellular network. So the app never sees the response. Naturally, the client, or the user who is now aggressively mashing the button in frustration, retries the request. Without explicit handling, retries against an eventually consistent system will result in catastrophic duplicate state. You just charged your customer twice. Ouch.
This is where idempotency comes in. It guarantees that executing the same operation multiple times produces the exact same end state as executing it just once. So, here are the concrete architectural answers to our double charge problem. First, natural idempotency. This means using operations that are just inherently safe, like an HTTP put that sets an absolute value rather than a relative increment. Second, deduplication tables. Payment APIs like Stripe do this by requiring the client to generate a unique UUID and send it as an idempotency key header. The server stores this exact UUID in a fast key value store like Redis, with a 24-hour time to live. When the client safely retries, the server checks Redis, sees the key, and just rejects the duplicate operation, returning the original cache response instead. And third, conditional updates. This is optimistic locking, where a database update only succeeds if the underlying row version number hasn't changed since the client last read it.
But of course, this safety carries a physical cost. Doing that mandatory deduplication table lookup to ensure an idempotency key hasn't been used before, that adds a physical 5 to 10 millisecond database penalty to every single mutating request that hits your API. Think about the paradox here. You are intentionally slowing down your average latency, literally adding overhead to every single successful transaction, specifically to guarantee systemic correctness during failure states.
Part 5. The real-world user impact. Performance as a feature.
So to verify our mental models of how these trade-offs actually perform, we use chaos engineering to define a baseline steady state. This means tracking a combination of business metrics like order volume, server-side saturation like CPU and memory, and client experience metrics like time to first byte. You absolutely must know exactly what your healthy system looks like mathematically before you can prove your architecture can actually absorb and adapt to injected latency.
We intentionally inject failures into our lower environments, like severing network connections between microservices or simulating massive cache wipeouts. We do this because we need to observe how backend replica lag physically manifests on a client device. Because it's not just about a server throwing an HTTP 500 error, it's visceral. It's about a user staring in sheer frustration at an infinite loading spinner. It's about checking if a lag in the pricing service causes the UI to flash full price before suddenly dropping to the discounted price, completely breaking the user's trust in the checkout flow.
And this brings us to a really powerful truth from engineer Nelson Elhaj. He says, performance is a feature in and of its own right, which fundamentally alters how a tool is used and perceived. Performance isn't just your best-case scenario on a fast fiber connection. If you're only optimizing for average latency and you're completely ignoring how tail latency, replica lag, and consumer rebalancing affect your failure states, are you actually building a system your users can rely on when the network inevitably hiccups? Think about exactly where your system's breaking point lies, and ask yourself, what really happens to the user when it breaks? Thanks for joining me on this explainer, and keep building resilient systems.